Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today I'll be talking about some sparse statistical estimation problems, and in particular how we go about solving the underlying computational issues. This is joint work with Sahand Negahban, who's at MIT, and Martin Wainwright at UC Berkeley. And this talk was prepared for a slightly broader audience, so if you guys feel like I'm belaboring some kind of obvious thing, feel free to let me know. So before I go into the details, I just want to motivate the kinds of problems with a couple of examples. The first one coming from the area of computational biology, where a common problem people want to address is, so we want to understand how a certain disease depends on the genome sequence of individuals. And the way they often, a common approach to try and approach this problem is we take the genomic data of a whole bunch of individuals. So n is the number of individuals, and each person's genome is one row of the matrix here represented as a long string. And maybe as a first start, all I'm going to try to do is to just try and learn a linear classifier to predict whether the person has a particular disease or not. And I've got some training data available where I know who has the disease and who does not have the disease. And I want to learn this for unknown persons. Now, the trouble, the reason this problem can be quite challenging is that this genome data is typically very high dimensional. So the exact number will depend on the particular representational choice and so on. But typically, these sequences will be at least on the order of a few 100,000 length string in the natural representation. And acquiring data in these problems is rather hard because you got to have willing volunteers, and then you have to actually sequence the data, which requires both time and money. So you might have just a few hundred samples that you have to work with. So, I mean, statistically, this would just be impossible if we were stuck with these numbers. Now, what comes to our rescue is the fact that, at least biologically, the intuition is that a given disease just depends on a handful of genomic markers, not really on a very large number of them. So I expect that there will be a pretty good predictor that has just a small number of non-zero entries, which will be able to do well in solving this prediction task. So I expect a sparse solution to be possible in this problem, even though I'm in a very high dimensional setting. Similar sort of theme comes up in signal processing, where I'm sure many of you have heard of the buzzword compressed sensing. The idea here is that I've got some signal that's again very high dimensional because, I mean, I've done a very high dimensional encoding because I don't want to lose information. And now I've sent this signal over a channel. I take noisy measurements of it, in particular just, let's say, noisy linear measurements of it. And I want to recover the signal back from these measurements. And again, here it's preferable to keep the number of measurements small because, I mean, the number of measurements here could correspond to the size of your antenna array, for instance. So you want to keep it as small as possible. But of course, in general, you cannot keep this number of measurements too small. Again, what comes to our rescue is the fact that natural signals like natural images, natural audio, video, these kinds of signals tend to have sparse representations in appropriate bases. So the signal will have a small number of non-zero entries only, and this allows us to get away with a very small number of measurements than if this were actually a dense vector here. So this sort of style of problems where we are in some high dimensional setting, but we have some underlying sparse quantity that we are interested in estimating will be the topic of interest throughout this talk. what we will see today is a particular work that tries to develop essentially a linear time algorithm that solves these sparse estimation problems. Statistically, the error of the method is really up to constants the best possible any method can obtain with that many measurements. And because it's linear time in the data, I would say that it really is statistically and computationally optimal in terms of its performance. So let's now try to go over the details a little more. So I'll start with formally setting up the kinds of sparse estimation problems we're interested in. I'll go briefly over some of the stochastic optimization concepts that we're going to need in the talk. And then I'll present our algorithm and some convergence and numerical results about the algorithm. So the basic setup is going to be, as I said, we're interested in some quantity that lives in that's a vector in R to the D, where D we'll think of as a pretty large number. So there's a high dimensional problem. What we don't know, of course, this quantity theta star, but what we have are n samples that are drawn IID from a distribution that depends on theta star. So for instance, these could be xy pairs where y is generated according to the sign of x theta star, or a noisy version of that, right? So that's our observation model. Now the key challenge in these problems is going to be that the number of samples we have is relatively small. It's actually much smaller relative to the dimension d. And so we need some structural assumption to go along, otherwise the problem would be statistically impossible. And the one we are interested in this work is that theta star has at most s non-zero entries, where s will be suitably small compared with the number of samples n. And that's just one example of a structural assumption one can make. There are definitely many other structural assumptions that are studied in the literature, but I'm not going to talk about those in detail today. So let's just try to warm our way up to the problem. So in typical machine learning settings, say we want to do let's see how we might go about learning these sparse parameters in the first place. So a common task in machine learning is classification, and one reasonably good algorithm to solve the classification problem is to solve the so-called logistic regression problem, where you have this loss function. If you haven't seen it before, don't try to read too much into the particular form. Just some quantity which is convex that we try to minimize, aggregated over our data samples, that captures how well our predicted labels fit the observed labels. Now the problem is this is not going to in general produce a sparse solution. So if you're interested in learning a sparse parameter, then you might be tempted to just throw in a constraint that says, oh well, I just want to estimate a quantity that minimizes the loss but has at most s non-zero entries, right? That's a pretty reasonable starting point. Similarly, in classical regression, we might try to minimize the least squares loss over the data samples. We might be tempted to throw in a sparsity constraint here as well. The trouble, of course, is that the sparsity constraint is combinatorial. It gives rise, these optimization problems written down here tend to be NP hard. So we don't want to attack them directly. Now, these problems, of course, are of great interest, and people have studied them at least for the last 20, 30 years, if not more. And one of the key realizations that has come in is that we don't need to work with the sparsity constraint directly. We can actually get to a pretty good surrogate for it in form of the L1 norm, which provides a convex relaxation for this constraint. And I'm going to go into the geometry of that in just a minute. So the L1 norm is just the sum of absolute values of the vector. And the kinds of problems that we are actually going to try to solve would be L1 regularized logistic regression. So we have the same logistic laws, but now we are also trying to keep the L1 norm of theta small as a surrogate for sparsity. Similarly, in sparse regression, we are going to try to keep the least squares loss small along with an L1 norm constraint to learn a sparse solution. Okay, a very quick poll. Are people comfortable with why L1 produces sparse solutions? Otherwise, I can go quickly over one slide about why that happens. Yes, no?
Slide would be good.
Okay, great. Okay, so this is a very toy example, but I think it gives good intuition about why L1 produces sparse solutions. So, even though we're thinking all the time about high dimensions, I'm just going to give a one-dimensional example to provide intuition. So, in one dimension, you can set up a very useless and toy problem, which is suppose I have a quantity theta star, and I look at the solution to the optimization problem of minimizing theta minus theta star squared over the single parameter theta. Of course, the solution to that is just theta star, right? So if I plot the solution theta hat versus theta star, I just get the straight line theta hat equals theta star, right? Now let's see what happens if we add an L1 penalty into this problem, right? So in one dimension, L1 penalty is just absolute value. And now if I look at the solution theta hat, the first thing to note is that there is a range of values between minus lambda and lambda. If theta star lies in that interval, my solution is 0. And outside that interval, my solution gets shrunk towards 0 by an amount lambda. But this part is actually really crucial, that when my solution theta star is small in absolute value, then it gets truncated to exactly 0. This truncation to 0 is why L1 is able to produce actually sparse solutions rather than things with a lot of small non-zero entries. And this intuition, even though this is a very toy problem, actually carries over to more complex problems and higher dimensional settings as well, and is the reason why L1 actually produces sparse solutions. Okay, now these L1 regularization algorithms from a statistical point of view have been studied quite well now, and we have a pretty solid understanding of how they behave. So in particular, if I'm interested in studying problems of this form, that I'm minimizing some loss function, and whenever I say a loss today, I'm really going to be thinking about convex functions in the first place with potentially additional properties that I'll describe as I go along. So I have some convex guy here, and then I have the L1 penalty. If I minimize this thing over my data samples, then under suitable conditions it can be shown that theta hat and theta star are actually quite close to each other, and the error scales as this quantity shown here. So it depends. The first thing you have to observe here is that it depends as 1 over n on the number of samples, which is kind of important. Tells us that as we see more and more data, our error is going down to 0. But more importantly also, this error only depends logarithmically on the number of dimensions. So what that tells you is that you can really have very high dimensional data, and your error will still be not too bad as long as the solution is sparse enough, as long as theta star is sparse enough. And in particular, you can indeed have n to be significantly smaller than d. N can actually be just on the order of log d in this setting. And furthermore, this is really the best possible error that is attainable under just these assumptions that I'm trying to estimate as sparse parameters, and I have certain structural properties that I'm not describing just yet. But really, this is kind of the best possible error you're stuck with.
What is gamma?
It's going to be the something like a strong convexity of the expected loss. Yeah, it's gonna come up in a couple of slides. Okay, so that's the statistical picture, but in any machine learning problem, that's really just half the story. Now somebody comes and tells us that this is a statistically great solution. The second thing we have to ask is, well, that's great, but how do I compute theta hat? Right. So in particular, theta hat there was described as a solution to a numerical optimization problem, and so I have to understand what is the complexity of solving that problem. And again, the key challenge is that, well, theta lives in RD, where d is big, and dimensions are not just challenging for statistics, also for optimization. So I have to be very careful about what choice of method I adopt. So something like, for instance, Newton method, which has just a quadratic complexity in dimension, will not be feasible here. As a result, something like interior point methods are also going to be a poor fit. You can make quasi-Newton methods work to solve these kinds of problems. So say something like box-constrained version of LBFGS, for those of you who are familiar. will work. And then there is, of course, a whole host of first order methods that people have tried to apply to these problems. And these are all good and valid approaches. But one thing that often creates a bottleneck in all these approaches is that the gradient computation is quite expensive. So let's see why. If I have to compute the gradient of this objective function here, well, I have to aggregate the gradient over n data samples, and in each data sample the computation I'm going to have to do is going to be roughly order d. So the gradient computation is order n times d, and maybe I do something like 20-30 iterations even, which is roughly maybe the least you're going to have to do. Incurring this cost 20-30 times can be quite prohibitive when n and d are scaled together.
Just one question.
Mm-hmm.
For typical data sets where d is large, if you're talking about,
Yeah.
it is observed that it's typically sparse, right?
The predictor is sparse, the data is not sparse necessarily.
Even for 100,000 dimensions. Like for example, let's take the genome example you are taking, right? So
Yeah, that data is...
the matrix of 100,000 dimensions.
Mm-hmm.
What do you think is the sparsity of that?
That data, the biology data tends to be extremely dense, because I mean the number of there is going to be an extremely large number of genes that are expressed. They may or may not be relevant to the problem at hand, but you don't know that. Similarly, in computer vision, I mean your features are so text is, for instance, one example where features will be sparse, and then you can exploit the sparsity of the features. But there are a host of other problems. So for instance, in a lot of signal processing settings, again, the features are not sparse.
So the assumption here basically, when you say order n d is...
Yeah, otherwise this will be like, say, the number of non-zeros in your data matrix. That can still, I mean, even with a decent sized text corpus, that total number of non-zeros in the data matrix is still pretty formidable quite often. I mean, if you have data where it's not big enough yet, odds are in 2 years you will have one where it is. So, you know, these things are, I think, important concerns. Okay, so with that sort of a concern, we're going to now kind of switch gears for a little bit and talk about basically a paradigm of machine learning that's been getting increasing popularity, that essentially tries to be better scalable for large data sets. So really that starts from the basics of our approach to machine learning. So typically what we do is, what we really are interested in is minimizing the expected loss function, maybe with the regularization penalty, and the expectation here is taken under the correct distribution, which I would like to recall depends on theta star, the unknown quantity. Right? So that is the guy I'm really after. But of course, theta star is unknown. I cannot evaluate this expectation. All I have is data samples. So I instead minimize my sample average loss and treat that as a good surrogate for the expected loss. And then I use statistical arguments to show that this procedure indeed does the right thing.
I'm sorry, I'm a bit confused about the first term aspect. What does it
So let's say you have the least squares loss. Then really what you're interested in is, if you take the true distribution that your data samples are coming from, so you know your x's and y's are being drawn from some distribution actually. Let's see, let's go actually all the way back here, right? So I've got an underlying data generating process. It could be something like the observations y's are x theta star plus some zero mean noise, for instance. Then statistically what you're interested in is minimizing the expectation of y minus x theta star squared. Not actually y minus x theta star over some data samples, because samples are just a surrogate for the distribution. And in the end, you want to talk about what happens over an arbitrary random sample drawn from the distribution.
So y and x are your, so y is your observations, right? Random.
Y's are observations and x's are the data vectors.
And y's are, you don't know where y's are coming from, what distribution they come. It's given to you.
Yeah, you don't know the distribution because it actually depends on the true parameter theta star.
So why does the distribution depend on that?
So in this case, for instance, the expectation of y given x is x times theta star, right? If this is zero mean noise, so the distribution implicitly contains information about theta star. Because if the distribution was completely independent of theta star, then how are you going to estimate theta star based on samples from the distribution?
So it's a sort of promise problem, that you promise that your y will look like x theta star.
Right. No, so y depends on theta star, I see that.
Yeah.
I'm having trouble understanding this notation of expectation.
So
what does it mean?
So okay, y depends, since y depends on theta star, as you agree, I can say that if I have random samples x, y, then the distribution they're drawn from depends on theta star, right? And so I'm just going to call that distribution p indexed by theta star, right? So it can, for instance, if I'm just observing, let's say I have just a single Gaussian observation, right? So I have some unknown mean theta star, and I observe noisy versions of that. So I have a set of probability distributions indexed by theta star, and by estimating the mean, I'm trying to get to theta star there. So this is just stating this that sort of thing a bit more generally.
Okay, maybe a bit more clarity.
So the point is, we are really, what we are interested in is minimizing the expected loss function. What we do is minimize the population loss and then the sample loss, and then hope that's a good enough surrogate. What stochastic optimization instead tries to do is directly attack the expected objective, rather than doing this two-step. It just cuts to the chase.
So just to clarify, this notation expected theta star refers to expectation over the distribution induced by theta star.
Yes, expectation under p theta star. Yeah, theta star is not a random choice. Yeah. Okay, so let's see how stochastic optimization can kind of go about this, because as I just said, theta star and hence the distribution defining this expectation is unknown.
Sorry, theta star is a vector?
Theta star is a vector.
What's the dimensionality?
D. So.
Oh, okay. Thanks.
Right. So the trouble is, I do not know the distribution, but of course, as before, I do have the ability to sample from this distribution. So the idea in stochastic optimization is we kind of try to use these samples to construct some kind of unbiased estimators, and then work our way with those unbiased estimates. So I'll just give a concrete example so that we can see how these kinds of things work. And this is perhaps the simplest stochastic optimization algorithm out there, called stochastic gradient descent. So as you might imagine from the name, this is very much like gradient descent, but instead of using gradients as in gradient descent, it's going to use stochastic gradients, right? So it's an iterative algorithm like gradient descent. You have some initialization. I'm just going to initialize at 0 for now, assuming it's in the set. And I'm interested in minimizing this quantity. At each iteration, what I do is I draw a sample from the distribution that defines this expectation, right? So I draw a sample xtyt. Then I compute the following update, where the important thing to, so this part is just the gradient, and I kind of wrote the gradient of the L1 norm, and she is frowning at me, so this is like, I'm just going to brush subgradients under the carpet for now. The important thing to note here is that if I were to actually take the gradient of my objective function, then I would need the gradient of this expectation, which I cannot evaluate. So what I do is I evaluate the gradient at just a data point that's drawn from this distribution. And of course, this, because xtyt is just a sample that I drew independently, and theta t is based on my previous data, this is going to be correct in expectation, this update. In expectation, this gradient is equal to the gradient of the expected loss. Right, so
So one last question.
No, go ahead.
In the genome example, how do you sample this XTYT?
So basically, this XTYT is the people who have come into my lab as volunteers. I have evaluated whether they have a disease, whether they have the disease or not, and I know their genome data. And now so at each time I'll take my logistic loss. I'll take, so the number of rounds here will be like, the T here will be like the number of patients I have. So at each time I'll take the data of the next patient and evaluate the logistic loss on the data of that patient, and then update my parameter, then move on to the next patient, evaluate the logistic loss and its gradient, and so on. Right, so I'm really just going over my data sequentially and once. This is an online algorithm. Now the key thing to kind of note here is that because this is a single sample gradient, this can be evaluated in time. That's O of D instead of O of n times D. And that can be immensely powerful because so we have made a considerable saving in the cost of each update. So now it all boils down to how many updates we're doing and how the aggregate math kind of stacks up. And we're gonna look into that in just a minute. But is everyone kind of comfortable with the basic algorithmic template so far? Okay, since you are comfortable, I'm going to make things a little more complicated and introduce just one more example of a stochastic optimization algorithm, which is quite essential here because we kind of build on it. So this is a dual averaging algorithm that was introduced by Nesterov in 2007. Again, this is not the most accurate treatment of the algorithm. I'm going to simplify a lot of things. The idea is that we can rewrite the previous update that we just saw using, instead of just one sequence, we can define two sequences. The first sequence mu is just going to maintain the sum of the gradients of some of these stochastic gradients. And then based on this mu sequence, I can write down my theta sequence as minimizing the dot product with mu t plus 1 plus squared plus an L2 norm squared with some appropriate step size sitting here. That's just equivalence by algebra. But now this form is useful because it immediately allows us to generalize the update rule a little bit. So in particular, first of all, we can restrict this argument to any convex compact set, and we will as we go along. And this is useful if you have constrained optimization. And also you can change the choice of the norm here. So there can be a very general thing that sits here, but I'm just going to today think about choices of LP norms instead of the L2 norm for p strictly bigger than 1 and less or equal to 2. And what happens when you substitute functions that are LP norm squared here are basically different values of p are good for essentially different assumptions on the geometry of the parameters theta. And I mean, we are in a structured sort of optimization setting here. We are assuming that we have sparse parameters. So the underlying geometry will actually dictate the choice of this p that gives rise to a good algorithm. So this generalization is quite important. Okay, now this is probably sort of the last technical thing before I actually get into the algorithm. So as I said, there are two parts to the update complexity. One is, of course, the complexity of each update, and then there is how many updates you actually need to make. So we've seen the stochastic optimization algorithms have per update complexity. What about the number of updates? So at a very high level, one thing that you have to be careful about with these algorithms is that you're working with these single sample gradients that have noise in them. So you have to make sure that your steps are not too big, because each step that you take is kind of a noisy step, and if you trust it too much, then you could land in very bad places. So a lot of wisdom built over many years has shown that at least if you set the step size to be roughly 1 over root t at time t, then your algorithm at least is going to converge properly. And in particular, in the settings that we are interested in, what we would like to study is the convergence of this average solution. So theta bar t is, sorry, I should have had a 1 over t there. So I'm looking at the average bit rate. This, it can be shown, gets close to theta star, the true parameter we are estimating, but we would like to understand the rate at which it gets close to theta star. And you don't have to take average over the entire thing here. In practice, you can take the average over the second half or the the last quarter or something as well. So the key reason why stochastic optimization algorithms have been successful and popular recently is actually there are many problems where a very striking phenomenon happens. What you can show is that this error is actually statistically, in an information theoretic sense, it's the smallest possible error from t data samples that any estimator can attain, not just a particular stochastic optimization algorithm that I'm using, but if you were to take those entire t samples that I use and run some crazy computationally infeasible algorithm even on them, you're not going to get a statistically smaller error beyond constant factors. And here is my stochastic optimization algorithm that has a complexity that's linear. If it's doing something very simple with each data sample, and it's getting the same error. So really, this is a very powerful statement. Now the precise behavior of this quantity, of course, is different for different problems, and it depends on the properties of my objective function. So I'm going to just quickly go over a couple of important properties that influence the rates. So probably everybody knows what a Lipschitz function is. If 2 points are close, the function value should be close, should not have jump discontinuities. But just one thing I would like to highlight is that even quadratic functions are not Lipschitz. In a global sense, you can make them Lipschitz on a compact set, but the Lipschitz constant will scale with the size of the set, so that can be a problem sometimes. The second important property is that of strong convexity. So a function is strongly so any convex function, first of all, we know it's above the first order Taylor approximation, but if it's strongly convex, then the gap between the function and the Taylor approximation depends on the squared distance between the points of interest. So basically this is saying that your function is lower bounded by a quadratic function. You can fit a parabola under it. And there is a choice of norm that you put on the underlying space in both the Lipschitz and the strong convexity, which is again something that you have to be kind of careful with in these situations. So very roughly, summarizing a lot of work done over the last many years, what can be proved is if the expected loss, so the L1 part, it's convex, it's Lipschitz. So we are mostly concerned, and it's not strongly convex. We are mostly concerned with the properties of the expected loss part here. If it's convex and Lipschitz, then we get a convergence rate that's roughly 1 over root t after t iterations. If the expected loss is strongly convex, then we get a convergence rate that's roughly d over gamma t. That should be a gamma squared. So this is faster than 1 over root t because t is big, so 1 over t is smaller than 1 over root t, but it grows linearly with the dimension. For convex Lipschitz functions, where we know that the optimum has only s non-zero entries, we can get s squared log d over t, whole thing under square root. So we can actually get logarithmic rates with dimension even in the optimization side of things. Now let's so that's kind of what's almost standard by now. Let's now take a step back, look at the problems we have, and ask what are the different properties of the objective that hold there, and what can we expect to have. So again, the two sort of canonical problems I've been talking about so far are sparse classification and sparse regression. And if you think about them a little bit, what you can show is that in both these cases, the objective is strongly convex and has a s-sparse optimum. Now that kind of, the moment you realize that, you're in a little bit of a fix. Using strong convexity, you can get a rate that's like 1 over t, but has a poor dimension dependence. Using sparsity, you can get a rate that has a great dimension dependence, but is 1 over root t instead of 1 over t. And it's a very natural question to ask, well, can I get both? I want to have a log d and a 1 over t scaling. And that's precisely the question that led to the work that I'm presenting today. We want to get both of these simultaneously. So I'm going to now present our algorithm that after some acronym gymnastics I managed to name radar. So the algorithm takes a little bit of a work to describe, so we'll go over it together with some pictures. What we require is we know some initial a priori upper bound on the L1 norm of the true parameter. I'm going to denote it by R1. It can be pretty loose, doesn't we have a very, very mild dependence on that quantity. What we're going to do is we're going to basically build on the dual averaging algorithm that I showed a few slides before. And recall that I stressed this point that the dual averaging can use p norms for an arbitrary p, and it is important to use a good choice of p here actually. The exact form doesn't matter so much. What's important is that it's pretty close to 1. You can think of it as 1 plus epsilon essentially. Right? So this and why it is close to 1, because I cannot take exactly 1. There are technical issues with that. So now here's the algorithm. I initialize at some point 0 for lack of a better choice, and now I'm going to run dual averaging for a while, right? So and in particular I'm going to use the more general form of dual averaging where I allow a constraint and I allow this regularization in LP norm. Now note that so there is a slight inconsistency here. What I assume is that I have this knowledge, but I restrict my set in P norm, and that's due to computational considerations, which I'll point out. But because P is very close to 1, doesn't really matter that much. But that's why I kind of show the constraint set to be this, not quite the diamond, which is the L1 ball, but slightly fatter with rounded corners. So that's an LP ball of radius R1 centered around 0. We know that theta star lies somewhere in the set because P is bigger than 1. So the ball is only bigger. Theta star will indeed lie in the set. And now I start dual averaging. I move somewhere, trying to get closer to theta star, hopefully. Now, traditionally, you'll just keep on running dual averaging for a long time, but this is going to give us a 1 over root t style rate that we're not happy with.
So each iteration is order t time, right?
Order dimension. Oh, and one important thing I want to point out here is that you should observe even my regularization coefficient here is lambda 1 now instead of lambda. So even there's going to be a critical rate of change of lambda that I'll point out as we go along. So this is not something I'm going to hold fixed. Okay, so I do this dual averaging for a while, but I don't do it until convergence or anywhere close to it. I just do dual averaging for long enough that I can guarantee that theta bar t minus theta star squared in L1 norm is at most R1 squared over 2. So initially I knew that when I started, my solution was 0. I knew that I'm R1 squared away from theta star. Now I know that I'm R1 squared over 2 away from theta star. So I've halved my error. And I say, okay, well, I'm going to stop what I'm doing for now. And I'm going to change things around a little. Right? I have this new information that I want to utilize. So I start a new epoch. And the idea is that, well, now I have this point that is provably a better candidate solution than 0 was. So why don't I actually recenter my constraint around this new point? I'm going to call it y2. So I now recenter my set around that point, but now I can take a smaller set, right? I can take R2, which is R1, R2 squared is R1 squared over 2. So I know that now my error is at most half of the previous error, so I can take a smaller set. I also decrease my L1 regularization amount. And this is kind of important. So initially you haven't really seen any data, so you regularize a lot, because otherwise you're not going to get a sparse solution at all. But now you've seen a bit of data, you can trust your data a little more, so you decrease your regularization a little. And this is important because this is carefully controlling the amount of bias you introduce into your problem. So you basically now recentered your set, you shrunk the set, you decrease the amount of regularization, and now you start a new epoch from this point y2.
So how do you know that the epoch is over?
Very good question. So for now, let's just think of it as we can actually test the condition knowing theta star, but in practice, of course, that's not what we do. There is essentially a version of the algorithm that's agnostic to the knowledge of any problem-dependent constants and still can guarantee whatever I'll describe.
You can run for one, so the error is quite large, right? So
yeah.
If you run for 1 by square root R1.
Yeah. Well, the problem is that there are some problem-dependent parameters that go into that error bound, like the strong convexity and so on, that you do not know. So you cannot trivially say that, oh, after this many iterations I have done enough work.
There is some non-trivial.
Yeah.
Sorry, can you go back just one slide? So here, here the constraint is the L1 distance, right?
No, LP. So okay. Let me point this out. The LP is very important.
The checking condition is L1 distance.
The checking condition is L1. I mean, the checking you can do in L1, LP, any of them. Again, the particular choice of P ensures that you're you're sandwiched basically between 1 and a factor of E. So it's not a big deal either way. The reason we pick P here is because this update as it is you can compute in closed form. But if you had a P here and a 1 here, then you'll have an order D squared update instead of an order D update. So it's just computationally very important to keep P here. Okay, so now we have this, we have initialized this new epoch, and now we do dual averaging again. The key things that have changed are now we are using a smaller amount of regularization. We have centered our set around y2, and we are using a smaller radius, and our regularization is now centered around y2 as well. And again, the fact that this guy exactly corresponds to this guy makes sure that you can compute your update still in closed form. Right, so now we just repeat this process over and over again. We run for a while, we have a certificate that we are closer to the optimum than we were before, and then we start a new epoch of dual averaging.
So why not do this like after every step?
Yes, that's a great question. The trouble is I don't know how to update this guy. So this guy you can come up with candidate proposals. I don't know how to update this guy. And I think that's actually a very interesting question. I spent a lot of time thinking about it. If you have thoughts, I'd be very happy to discuss more.
Again, can you explain what do you mean not update?
So Pratik was asking, why do I, chunk this into discrete epochs? Why don't I just...
Right.
The trouble is that basically, so my epochs are designed in such a way that after each epoch I know that, oh, now my new radius should be like 1 over root 2 times the previous radius. But if I take just one step and I want to update my constraint, I don't know what the new radius should be. So I don't know how to shrink the set. Basically, that's my problem, and I try to. Yeah.
So this lambda has to keep changing, right? So how is it related to the original lambda ability function actually?
So think about it this way. There is no original lambda, right? When I got the problem, I was told, there is an underlying theta star. Your job is to estimate it. So now I'm allowed as a statistician to construct whatever set of problems I want. as long as I can guarantee that I eventually get theta star. And so that's the idea here, that I'm basically constructing a series of essentially related problems. And at the end of the day, I'll guarantee that in doing so, I estimate theta star. The issue is that basically, if you think about solving the original problem, so the expected loss plus a particular value of lambda, then the amount of error you incur depends on lambda. Now, okay, so you can either choose a big lambda or a small lambda. When you choose a big lambda, then you have too much bias. If you have a small lambda, then you'll not enforce enough sparsity, and especially for stochastic optimization, because initially you've seen very little data, you'll really have not sparse solutions. So you can, I mean, this becomes an empirical issue actually. Theoretically, you can still kind of say that, oh, you lose only a little bit in the constants and so on when you try to use a fixed choice of lambda, but empirically that creates a difference. And yeah, so, oh, not log d, sorry. That would be phenomenal and impossible information theoretically. Okay, so that is the algorithm.
Just one more question. Intuitively, why is P great? I mean, you change the norm to P rather than 2, right? I mean, I still don't have the intuition. Why should that intuitively? I'm not
okay, so
why should it do better? What structure is it imposing, right?
So think about basically this ball, and particularly if this ball were an exact diamond even, right? Versus this being a sphere. The sphere has no corners. So when you project down onto a sphere, you land somewhere in the orth end. When you project onto this ball, you're likely to, okay? Okay, so now, I mean, the main interest in this optimization algorithm is about the convergence rates it's able to get and the performance it is able to produce on the problem. So I want to spend the remaining time on those aspects of the algorithm. So I'm going to present a very simplified form of the results. Let's assume that the expected loss is Lipschitz and strongly convex. Let's assume that the true parameter theta star indeed has at most s non-zero entries. Then with high probability, after t iterations, so this is, now like I'm summing iterations over all the various epochs that I might have performed. Overall, if I have done t updates in my algorithm, then the error will be at most, ignore these quantities for a minute. The dominant term here is s log d over t. So we have the initial goal we set out with of having both a logarithmic dependence on dimension and a 1 over t dependence on the number of iterations.
Is R1 something like poly T? R1 in your...
It really depends on what you know about the problem. I mean, it's a... So you may assume some natural scale, like if you expect your theta star will have a small enough L2 norm, then yes, R1 can be something like root D. You know that will work, provably. But if you, it really depends on what is a reasonable assumption about the problem you have at hand, based on the data you have. I can tell you how to construct estimators for it, but I cannot really. I think L2 norm 1 is often a pretty bound L2 norm constant is often a pretty reasonable assumption. In fact, then R1 will only be root s because it's an s-sparse quantity theta star. So that might be a good ballpark to keep in mind. So as I said, this is a very simplified form of the results. In particular, the results do not require theta star to be exactly sparse. It can be approximately sparse. So you can have very small non-zero entries as long as you have some appropriate decay rate and so on. One important thing to consider is actually things that are not globally Lipschitz, but things more like squared laws that that have Lipschitz constants depending on the domain, and we can extend the arguments to that. Qualitatively, the result looks very similar still. Now, initially I said that this algorithm is optimal in a certain sense, and so I want to just explain that a little bit more. So what we are guaranteeing here at a high level, forgetting everything else, is that our error is going to behave as s log d over gamma squared t after t iterations, where gamma is the strong convexity. So the thing again to keep in mind is that the stochastic gradients we have can be computed from just one sample. So the number of samples and iterations is really equivalent in this case. So I might as well say that I have an algorithm that produces this much error after looking at t statistical samples. Right? Now this is where this becomes very interesting, because for problems of this form, at least for interesting special cases like logistic and squared laws, the information theoretic limit is already known statistically and says that no possible method can produce an error that's smaller than this quantity after observing just t samples. So really this is up to constants, the best possible error that any method, any potentially computationally hard method can also get, and we are obtaining that error in linear time. So that's why I made somewhat bold claim initially that in some sense this is statistically and computationally optimal algorithm for solving the particular problem at hand.
But I wonder, because your objective function is both Lipschitz it's both Lipschitz constant and strongly convex, right? So in some sense it's very strongly bounded. So if I just did a simple batch optimization, I would get after log 1 over epsilon iterations, I would get error which is epsilon, which is the same as doing n times log 1 over epsilon passes through the data.
Yeah.
It will be the same computational complexity that you have. Right, because you're just amortizing over t iterations, so your complexity is d times t,
right,
and my complexity is n log d.
And d log 1 over epsilon. Yeah.
N d log 1 over epsilon. So
right. But I can do with t equals n, right? So I have nd. The batch method will at least have nd log 1 over epsilon. 1 over epsilon will be, if you have to do the
epsilons will be different because your error is dependent on s log d over t.
Yeah. So you'll have to, exactly. So you'll have to actually minimize it at least to something like s log d over n again. So you can just think of log 1 over epsilon, you can think of it as another log n, right? That's a very reasonable assumption, I think, because I at least got to solve it to statistical precision.
We'll talk.
Yeah, we'll talk. So I mean, I'm not saying that this will, if you really work hard to design the best possible batch algorithm, it's going to necessarily always perform better. But first of all, it does, even in experiments, do quite well, and it is in its own right, it's optimal. You might be able to construct something else that's optimal as well, but
typically how many passes do you do through the data?
In all my experiments I did one. So I mean, at least when I played around a little bit, I mean, I don't have any evaluation against batch algorithms in this in the simulations today, but from my past experience they definitely tend to take longer. So in the simulations we looked at only sparse linear regression problems, which as I mentioned before is not Lipschitz but can be handled with an extension of the analysis. So we basically were interested in two sets of benchmarks. So two important ones are a version of the dual averaging algorithm that basically exploits the sparsity properly and gets a 1 over root t style convergence rate, but depending on sparsity, and a version of stochastic gradient descent that adapts to the strong convexity of the problem and gets a convergence rate that's like 1 over t but does not depend on the sparsity of the problem. And then we wanted to compare it to our algorithm, which tries to exploit both. Now again, with our algorithm we evaluated several different versions. So what I call radar is kind of the idealized version, where we really just set our epochs based on the knowledge of theta star. So we actually evaluate the error and check. When it's been halved, that's when we initialize a new epoch. It's just the theoretically ideal version of the algorithm. And then a couple of different variants. So what I call EDA or epoch dual averaging here is actually something that's very much based on a related earlier work of Lipschitz and Nesterov, and that's kind of like radar in the sense it's also an epoch based algorithm. It does not change the regularization the way we do, and we still gave it the exact knowledge of theta star to set the epochs. And then radar const is the one that we actually can run on data, which does not use the knowledge of theta star or other properties that are inaccessible to us, and sets its epochs just in a purely data driven fashion. And report results averaged over 5 random trials. So the first set of plots compares just the ideal version of radar to the other stochastic optimization benchmarks from before. And here we kind of get a comprehensive win. We see that actually in this case it is very important to exploit the sparsity of the problem, even if you don't exploit the strong convexity, in fact. So RDA already beats stochastic gradient descent by quite a bit, even though it was not exploiting strong convexity. And we observed this we tried 2 different sizes of the problem. Now,
what are the number of examples here?
It's the number of iterations, right? So it's growing as we go along, right? Because each iteration is based on a fresh sample. The second plot is a much more careful comparison because things are significantly closer here. So what we see is that radar definitely. So first of all 3 are, good methods that adapt to both the structural things here. So all of them have a pretty good performance, I would say. The ideal version of radar still beats the ideal version of EDA. Both of these are using some information that we do not have access to in real life and can only do in simulation. And then there is the radar constant, which is almost as good or sometimes beating EDA a little bit, but definitely worse off than our most ideal algorithm. So the bottom line is that we are able to exploit both the properties. We lose a little for not knowing things about the problem that we would ideally like to know, but that is life. We don't lose too much. Vishy?
So what's the sparsity of these problems?
About log D.
About log D.
Yeah.
So it seems that radar is showing some action only after.
Oh, this guy, yeah. So that is a very that's a very subtle point. So what happens is essentially what happens in this algorithm is because we don't know theta star, we are not able to terminate the initial epochs as fast as. So initially the epochs should be very short because you want a very coarse accuracy, right? But you end up kind of being very conservative about that, and so what happens is that you don't make very much progress initially, but because your algorithm is not very confident about what it's doing, but after a couple of epochs then it really picks up.
So your n is actually not much smaller than t.
It depends on which point in the plot.
I'm interested.
Yeah, if you look at the very end, it is pretty.
Point where your radar const starts.
No, it's related to what she was asking, right? You said one epoch, right?
Right.
So when you talk about 100 samples, then where will you get?
100 samples.
Because you talked about a case where n is far less than d, right?
Right.
D 20,000.
So so
that's where you have typically done resampling.
Right. So again, in this case, I don't remember what was the amount of strong convexity we were using again. So So yeah, the exact number of samples that you will be able to get away with will also really strongly depend on the strong convexity level. And
so these are all just regression, right? So you can control the strong convexity.
yeah. Yeah. I mean, even for classification, you can, like, if you're using logistic, you can do it through the link functions. Okay, so I'm out of time, so maybe I should skip this and just go over to the conclusion. So, yeah, what we saw today was a stochastic optimization algorithm for addressing these sparse high-dimensional problems. The main issue was to try and simultaneously exploit both the underlying sparsity and strong convexity properties, and it has information theoretically the optimal rate of convergence possible. And the nice thing is that the for a lot of common problems you can actually compute the updates in closed form, so that's pretty important. And even though I talked exclusively about sparsity today, the results also extend to a variety of other low-dimensional structures, such as group sparsity or low-rank matrices, in very natural ways. So that's all I had to say. Thanks.